get A and B, n times n matrix. We say that A is similar to B if there is invertible n times n matrix B, such that just satisfy this condition. We're going to say A similar to B if there is invertible matrix P. Invertible, we already know what's the meaning of invertible. That means there is an inverse of this matrix. So you see, P is the matrix, there is inverse for the matrix. When you multiply P inverse with the A, with the P, it's going to be exactly the same matrix P. Then that's how we're going to say A similar to B. How? We need to find a matrix P such that the inverse times A times P is going to be equal to B. Here is just a simple example about that. Here is the matrix A, and here is the matrix P. Here is the P. I already here just showing you. A, B, and here is the matrix P. This is invertible matrix. That means there is inverse. There is the inverse for this matrix. So when we multiply the inverse with the matrix A with the P, the result is going to be equal to B. There is the multiplication of PC3 matrix. The result, you can check that using the calculator, it's fine. It's going to be exactly the same matrix B. That's mean A similar to B. Okay, here is the theorem, and we're going to do another theorem. I'm going to show you where's the important things we're going to use. This is a theorem we're not going to use that much a lot, but just showing you if A and B and C, three matrices, A similar to exactly the same matrix, which is fine. If A similar to B, that means B similar to A. If A similar to B and B similar to the C, that means A similar to the C. Just makes sense. Just let me know. I'm already recording this one. I'm going to post it on Canvas. Let A and B n times n matrices with, here's a condition. They're telling you A similar to B. Then, this is another thing to prove that A is similar to the B. If A is similar to the B, that means we have exactly the same determinant. So this is another condition. If they're telling you prove that A is similar to the B, what we're going to do, we're just going to find the determinant of A, find the determinant of B. We have to get exactly the same determinant, that being A similar to B. A is invertible if and only if B is invertible. That means there is inverse for A, so it's going to be there is inverse for B. A and B have the same rank. Because imagine we're saying that A similar to B. That means A invertible, B invertible. Determinant of A equal determinant of B. The rank of A is going to be the same thing rank of B because they are similar. And A and B have the same characteristic polynomial. This is the important thing. We're going to use this one. Let's start on this one. 5. A to the power m, similar to B to the power m for all integer m greater than or equal to 0. This is the last thing on this section. They're going to ask you to compute like A to the power 10. How we're going to find that, okay? We're going to do an example. If A is invertible, then A to the power m similar to B to the power for all integers n. There is a proof for all these. We're not going to focus on the proofs. This is the important one. We're going to see how to find a matrix for power from any power. That means it's only the diagonal contains numbers. Like let's say here A, B, C, and the rest is going to be what? zeros. Keep this one in your mind. How are we gonna find that? We go in here, we have to find the P. Okay? I'm gonna show you how to find the P. Diagonalization and n times n matrix is diagonalizable if there is a diagonal matrix T such that A is similar to this matrix. See, we go back to the similarity. How we gonna find the diagonalizable? If there's a matrix D such that A is similar to the D. Yes, A is similar to the D. That's mean we need to find a matrix P. So the inverse times A times P is going to be equal to D. Again, until now, we don't know how to find the matrix P. So here's still the problem. Okay? You know what's the meaning of similar? Now we know what's the meaning of diagonalization. That's mean only the diagonal on the matrix is going to be numbers, the rest is going to be zeros. And what's the meaning of diagonalizable? That's mean there is a matrix T such that the matrix A similar to the matrix D. Again, we need to find a matrix P such that P inverse times A times P is going to be equal to D. Okay? Now, here's the important theorem. I kept exactly the same number if you want to check it on the slides from the book. It's theorem 4.2. It's exactly the same thing here. This theorem said, let A be n times n matrix. Then A is diagonalizable if and only if A is n has n linearly independent eigenvectors. This is the general theorem, but they add an extra acceptation. Eigenvalue, eigenvector. You see, we're gonna go back to the previous section. As we need to find the eigenvalue and eigenvectors. There exists an invertible matrix P. This is the important part. There exists an invertible matrix P and a diagonal matrix T such that, okay, P inverse A times P equal D if and only if the columns of P are n linearly independent eigenvectors of A. So they're telling you P is what? Is the n linearly independent eigenvectors. That means we're going to find the eigenvectors for A, which is the matrix P. You see, that's the important line here. They're telling you, okay, go ahead, it's n linearly independent eigenvectors, which is the matrix P.
So, say you get multiple eigenvectors, is that, do they combine to make T? Or
yes, we're gonna combine, because like, you know, the lambda, we're gonna go further and we'll see what's the meaning of lambda.
Okay.
Like, for each eigenvalue, you're gonna get eigenvectors. Put these eigenvectors together in a matrix, this is going to be the P. Okay? And here's the thing. And the diagonal entries of D, this is also important thing, of D is the result of multiplying P inverse times A times P, we're going to get the matrix D. The diagonal for this matrix is going to be what? The eigenvalues, okay? That means it's going to be like this. It's going to be the eigenvalues, okay? So, if I ask you just to find the T, the diagonal matrix, okay? Do you need to find P? No, you just have to find the eigenvalues. Find the eigenvalues and go ahead, put down the D, because this is the theorem that says the eigenvalues is going to be the diagonal of D. You got it now? So this is the important term. You see, I corresponded to the eigenvectors in P in the same order. Just gonna put it on the eigenvectors of P. That's mean P is going to be equal V1, V2, and V3, which is the eigenvectors. What they're asking you, determine whether A is diagonalizable or no. So the first thing, we're going to find the eigenvalue. So find the eigenvalue, which is exactly the same way we learned on the previous section. Determinant of A minus lambda I is going to be equal to 0. That's the determinant. Write down A, which is 2, 0, 2, 0, 2, 2, 2, 2, 0, minus lambda 0, 0, 0, lambda 0. Everything is going to be equal to 0. Okay? That's E here. It's going to be 2 minus lambda 0. And here is going to be 2. This one is going to be 0. 2 minus lambda. Here's 2. And here's 2. 2 and and how we're going to find the determinant for this matrix? Here is the important thing. You see, this is basic steps. You have to be careful here. Plus, minus, plus. I did that in details. So the first thing is going to be 2 minus lambda. Cancel this all, this column. So it's going to be 2 minus lambda, 2, 2, and negative lambda. Minus, this is 0. That's mean we're not going to care about everything inside. But the second number is 0, so they cancel everything. Plus 2, cancel this all, column, this all, so it's going to be 0. 2 minus lambda, and 2, 2. Now we're going to multiply these cross. So it will be 2 minus lambda multiplied by 2 minus lambda times negative lambda. So it's going to be negative 2 lambda. We're going to multiply right away. Plus lambda squared minus 4. This is cancelled here. Plus 2, 0. Here is going to be minus 2, so it will be minus 4. Minus 4, minus 2 like that. Plus 2. Then multiply everything here. So it's going to be so now we're going to multiply these two. 2 times negative 2 is going to be negative 4 lambda. 2 times is going to be plus lambda squared. 2 lambda squared.
So we're just multiplying by the determinant of, so, from going to, not that step, this, from,
this step.
yeah, it's, the determinant of that 2 by 2 matrix. That we're
Yes,
multiplying.
here.
Yeah.
Which is the cos, multiply cos.
Right,
This times this minus 2 times 2.
okay,
Same thing here, because this is the determinant of this matrix. 0 times 2 is going to be 0,
right,
minus this one is going to be minus 2 minus lambda times 2.
right,
Okay, so it's going to be -4 plus 2 lambda. Okay. So let's keep going. Yeah, don't let me move to the next step if you have an issue. So 2 times -2 lambda is going to be -4 lambda. 2 times lambda square is going to be 2 lambda square. 2 times -4 is going to be -8. I don't know if I have some mistakes here. Plus 2 times -8. Oh no, we have to multiply the lambda. So negative lambda times -2 is going to be plus lambda plus 2 lambda square. Negative lambda times lambda squared is going to be minus lambda cubed. Negative lambda times -4 is going to be plus 4 lambda. Okay, we're done from distributing these two parentheses. Now, 2 times -4 is going to be -8. 2 times is going to be 4 lambda. Now we're just going to combine the like terms. I have -4. I have 4 cancel. We have 2 lambda squared. 2 lambda squared, so it's going to be 4. -8. It's negative. So negative lambda cubed plus 4 lambda squared with this one, plus 4 lambda minus 16 equals 0. Now here's the important thing, because I know I forgot. How we gonna factor this polynomial? It's a cubic. That's the important step. That's why I did this example. The first thing we have to start from the possible zeros. We can't use the 0, 0, 0, 0, 16, not equal to 0, so we can. Let's start. 1, you're gonna start 1 or -1, that's not gonna work. 2, if you start with x equal 2 or -2. So if you said lambda equal 2, if you plug in 2 here, 2, 2, 2 is going to be, everything here is going to be 16, minus 16 is going to be equal 0. That means when lambda equal 2 is going to be 0. But until now, we didn't factor it. We need to factor when we see all the lambdas. So what I'm going to do, so just refresh your memory. So this one is going to be lambda minus 2 equal 0. Let's start with -2, which is the same thing. That means this is the first 0. This is the first, you have to plug in the number and to get the other side equals 0. Now we're gonna do the scientific division, or you can do the long division, it's up to you. Check what I'm going to. Do you have missing term? Cubic, squared, 1, 0. There is no missing term. I'm going to write down the coefficient here, which is -1, 4, 4, -16. Okay? The next step, I'm going to divide everything here by -2. Because this is a zeros, this is a solution, right? So This is one of the lambda is -2. So I'm going to divide everything by -2. This is the scientific division, not the long division. If you want to use the long division, it's fine. Okay. So write down the first number, then multiply this one by this number. -2 times -1 is going to be 2. Then add these two numbers. It's going to be 6. Okay? Go back again. -2 times 6 is going to be -12. Add these two numbers. 4 plus -12 is going to be -8. Now -2 times -8 is going to be, add these two numbers, is going to be 0. If you didn't get 0, that means -2 is not a root, okay? You have to get 0, this is important. If you get a number here, that means cancel this one, go ahead and use the 2 and keep going. If 2 is not gonna work, you're gonna use 3 and -3. If it's not working, you're gonna use 4 and -4 and keep going, okay?
So you just keep going, trying to find an initial root.
Initial root, so I can divide it by.
Yeah.
So now check how it's going to be easier. This is the first root, right? So I'm going to write down the first root, which is lambda plus 2. How am I gonna write down the result? Check here. This is the constant. This is x. This is x squared. X squared, x constant. That means I can open parentheses. I'm going to say this is -x squared, which is 1, plus 6x minus 8 is going to be equal to 0. I just need to find one root, so the rest, check is quadratic. I can factor it by using any method you can use. So now this is lambda plus 2. I'm going to open another two parentheses, equals 0, and it's going to be here what? I can say negative lambda plus 2, and here is lambda minus 4. So now we have 3 lambda. Lambda is going to be equal to -2. Lambda is going to be equal to 2, and lambda equal to -4. Look to the video again. So when lambda equal -2, that's mean a minus -2 with the I is going to be equal to the 0. We're gonna plug in lambda here to find now the eigenvalue. So it's going to be 4, 0, 2, 0, 4, 2, 2, and 2, 2. Everything here is equal to 0. Now by reducing, okay, by reducing that, use the whole echelon form, okay? This one is going to be reducing part, which is a minus -2 with lambda with 0, which is going to be equal. Going to reduce here 4, 0, 2, 0, 4, 2, 2, 2, 2, and here is the reducing. It's going to be by using the row echelon form 1, 0, 1 over 2, 0, 1. I'm just going to give you the results. 0, 0, 0. Okay, so the reducing here. Don't confuse yourself. Now, we're just gonna find the eigenvectors. So x1 plus half x3 is going to be equal to 0. That means x1 is going to be negative 1/2 x3. Okay? x2 plus half x3 equals 0. That means x2 is going to be negative half x3. Okay? So the eigenvectors is negative 1/2 t by, of course, by let x3 equal t. Negative 1/2 t and t. We can cancel the fraction, which is exactly the same thing if you write down negative t, and 2t. On the same time, you see this is the eigenvector. I'm going to find the base. If they ask you to find the base, so just let t equal 1. That means the base is going to be negative 1, and 2. See, I did 3 times, like we already have the eigenvalue. There is the eigenvector. Okay, base is going to be just let the t equal 1, so it's going to be negative 1, and 2. Okay. Any question? And do the same thing when lambda equal 2. Write down these. So again, when lambda equal 2, I'm going to plug in 2 here. 2 minus 2 is going to be 0, 0, and 2. 0, here's 2 minus 2 also is going to be 0, and here's 2, 2, 2, and negative 2, okay? So here's the matrix is going to be, I'm just gonna write down A minus, and lambda equal 2 with the I. That's mean this one is going to be equal, the matrix is going to be 0, 2, and 2, 0, 0, 2, 2, 2, and negative 2. This is the matrix. Now what I'm going to do, I'm going to reduce this matrix. I'm going to say A minus 2 with the I, with the zeros to find the eigenvector. It's going to be 0, 2, 2, 0, 0, 2, 2, 2, and negative 2. How are we going to reduce that? Check here, 0. I just need to compare this one to 0 and compare this number to 0. So by reducing, it's going to be, I'm just going to give you the result. By reducing, that's mean you're going to reduce it to the using co-echelon form, okay? So convert this one to 0. And again, we can switch this row with this one, it's going to be fine. Convert this one to 0. You multiply by 2, so we switch the first third row with the first row. Yeah.
But shouldn't it be 0, 0, 2 for the first row
0,
and the second row?
Oh yeah, this one 0. Yeah, the first one, the second one, definitely. Yeah, because here's is already 0. And this one, 2 minus 2 is going to be 0. Okay. So now we're going to switch the third row with the second row, and again you reduce it by using the row echelon form. The result is supposed to be 1, 1, 0, 0, 0, 1, and all zeros here. Okay, that's me. X1 plus X2 is going to be 0. So X1 is going to be negative X2. And X3 is going to be equal to 0. So the eigenvector, let X2 equal T. The eigenvector is X1, which is negative T. X2 is going to be T, and X3 is 0. The base, just let X1 equal and T equal 1. We need to find base. That's mean the base is going to be negative 1, 1, and 0. So let's go back. P is the eigenvectors. That's mean here is the first column for the P, and here is the second column for the P. Okay? You need to do the third P by using lambda equal 4. So when lambda equal 4, again we're going to plug in.
Negative 4.
Oh, sorry, negative 4. Good. So maybe A minus 4 lambda as the matrix is going to be. So it's going to be equal negative 2, 0, 2, and 0, negative 2, and 2, 2, 2, negative. Then by reducing, I'm going to say A minus 4 I with the 0, which is going to be equal. So I can use by using row echelon form. Negative 2, 0, 2, 0, negative 2, and 2, 2, 2, negative 4.
Are you sure that's negative 4?
Yeah, shouldn't it be plus 4i?
Plus 4i. Yeah, the main thing here, this is just like, we're gonna plug in the lambda equal negative 4 here,
Right.
okay? To get this one.
Because if it's a minus lambda I, it'd be a plus 4
So
or a plus lambda.
to make it,
Because you put
it's
negative
supposed
4.
to be get negative the lambda. Back here. Oh, because here's the wrong thing, you see?
Yeah.
Lambda equal 4. Because I remember I got lambda equal 4. So here is the wrong thing. If you go back there, you can see it. So the first page, so lambda minus 4 equals 0, that's mean lambda equal 4. Okay? So this is positive 4. So by reducing now from here, so this one is going to be the steps on the online assignments. It's going to be less than these steps. you have to use, it's going to be 1, 4, -1, 0, 1, -1, here is 0, 0, 0, 0, and 0. That's mean x1 minus x3 is going to be equal to 0. So from here, x1 is going to be equal to x3, and x2 minus x3 is going to be 0. So also x2 equal to x3. So if you let x3 equal t, that's mean the eigen vector is going to be all t's. Okay. Find the base by let t equal 1. So 1, 1, 1. So you see all these steps until now, we have proved that A is diagonal matrix. So now P is the eigenvector 1, the eigenvector 2, and the eigenvector 3, which is equal. The first eigenvector here we found it is -1, -1, 2. The second one is -1, 1, 0. And the third one is 1, 1. This is that matrix P. Okay. Again, we need to find what? Because we need to prove A similar to D, the matrix T. So we're gonna find the P inverse. The P inverse, which is -1/6. It comes out. -1/6. -1/2. 1/2 and 0. 1/3, 1/3, and 1/3. So this is the P inverse. Now the last thing, we're just going to use the theorem to find the matrix T. Now I'm going to ask you, can we find the matrix T without using the theorem? The theorem is one step of the theorem. It says the matrix T is what? The diagonal is going to be what? The lambda. Okay. So what's the lambda for the first one? -2. That means 0, 0. The lambda for the second one is 2. 0, 0. The lambda for the first one is the 4. So it's going to be like this. This is the matrix T. We're going to check that. The last thing by the theorem, because here's the thing, when you do the online assignments, they're going to ask you to write down P, the matrix P, and they're going to ask you to write down the D. Okay? That's what they're going to ask you to write down. So you have to find the P exactly the same method, but to write down the D, just go ahead and write down the lambda. But by the theorem, if you multiply the P inverse times the matrix A times the P is supposed to be equal to this matrix, which is D, okay? That's mean if you multiply the matrix P inverse, which is -1/6, -1/6, -1/3, 1/2, 1/2, 0. You multiply this matrix by the matrix A, 2, 0, 2, 0, 2, 2, 2, 2, 0. the matrix P, which is this one, -1, -1, 2, -1, 1, 0, 1, 1, 1. The result is going to be equal 1. Okay? This one is just like a shortcut. It's really important because before you move on, when you find the lender, you will know this matrix, you can diagonal this matrix or no. Okay? You can check that. So what it says, if A is n times n matrix with n distinct eigenvalue. What does that mean? A is, you got it? So it's really important because if you go back to the previous example, we have lambda equal -2, 2, and 4. So that's mean I can write down D right away, just put down zeros, and the diagonal is going to be the lambda. Okay? So this is also important because they're going to ask you on the online assignment, find the solution. Or they're going to ask you this matrix is diagonal matrix or no. So when you're going to find one of the lambda 1, lambda 2, exactly the same lambda, like -3 or 3, let's say 3. That's mean you're just going to, this matrix, you can be, it's the diagonal matrix, so just no solution. Okay? So the lambda is supposed to be different lambda. Before, one more example, they ask you to compute A to the power of 10 if A equal 1, 2, 0, negative. Okay? We'll do exactly the same process. I'm going to use the A, find the eigenvalue, find the eigenvector, find the P. Everything is going to be on the last step. You can do a shortcut. Don't do something shortcut here. Have to do all the steps again. It's not allowed for you to do all steps. Sorry. So the first thing, exactly the same thing, determinant of A minus lambda I is going to be equal to 0. That's mean A, which is 1, 2, 0, -1, minus lambda 0, 0, lambda equals 0. Now, the determinant of 1 minus lambda, 2, 0, and -1 minus lambda is going to be equal to 0. That's mean is going to be 1 minus lambda times -1 minus lambda. Okay, equals 0. Here is going to be 1, -1 minus lambda plus lambda plus lambda square equals 0. Cancel these. So -1 plus lambda square is going to be 0. That's mean lambda squared is going to be 1. Lambda is going to be plus or minus 1. Two different lambda, that's mean okay, this matrix is diagnosable. Now when lambda equal 1, let's find the eigenvector. So lambda equal 1, that's mean we're putting 1 here. So it's going to be 0, 2, 0, -2. Okay. Now A minus I with the 0. Plus 1 here. It's going to be 0, 2, 0, -2. Here's 2 zeros. By reducing so we're going to cancel this 0. This one is going to be, and convert this one to 1. So it's going to be 1. Zero, 2, 0, 0, 0, 0. Because we just cancel this one by adding these two numbers. That's mean 2x2 is going to be 0. So x2 equals 0. x3 is going to be any number. x1. And x1 equal t. That's mean the eigen vectors is going to be equal t and 0. Base is going to be by let t equal 1. So the base is going to be 1, 0. Here's the first one. So we're doing exactly the same steps. So when lambda equal -1, I'm plug in -1 here. That means it's going to be -2. And here's 2. This one is going to be 0, negative plus -1 plus 1 is going to be 0. So A minus I is going to be with the 0. That means this one is going to be -2, 0, 2, 0, 0 with the 2 zeros equal. By reducing, how are we going to reduce that? I just divide by 2. That's mean this one is going to push the same thing. You don't actually do anything. -1, 1, 0, 0, 0, 0.
How did you get -2, 2?
-2, 2. I'm plugging -1 where here.
Right. So 1 minus -1 should be 2.
1 minus -1. Oh yeah, this one's 2. -2, 2, and this one also, yeah, this is 0. So it's going to be 1, 1. That's mean x1 plus x2 is going to be 0. So x1 is going to be negative x2. Let x2 equal t. So the eigen vector is going to be negative t and x1 is negative x2 and t. Base by that t equal 1. So the base is going to be -1. So until now here, this is all the steps from the previous section. P is going to be what?
1, 0, negative.
P is going to be
1, -1, 0.
no, the first one is 1, 0.
Right.
So 1, 0, -1, 1. Okay, P inverse is going to give you the P inverse, which is 1, 1, 0, 1. So here is the thing by using theorem, this theorem, the third one. We need to find, it says P inverse times A times P equal D. Okay? That's me. P inverse I'm gonna multiply these. You want to check it. That's the P inverse, which is 1, 1, 0, 1, times the matrix A, 1, 2, 0, negative 1, times P, which is 1, negative 1, 0, 1, is going to be equal to the matrix D, 1, 0, 0, negative 1. Okay? You can check that. You see the matrix D? Here's the eigenvalues. Now, here's the same thing. Can I say A P inverse times A times P equal D? Can I say A equal P inverse D times P? That's mean this one. If you take in the inverse for both sides, the inverse is going to be here, the P is going to be the same thing. So A to the power 10 is going to be P inverse D to the power 10 times P.
Now, how are we getting A equals P inverse times D times P?
Okay, so let's do this one on the side.
Is it because it like a similarity or?
Oh yeah.
Yeah.
Oh yeah. Because when it's similar, that's mean A similar to D.
Right.
So I just can move these two here. You got it? Or if you're doing just like a matrix, if like just like make it simple. Use equal D. Now, if I multiply both sides by P, so P inverse A P is 1 times P, okay? Equal D times P. Can I cancel this one with this one? Because this is with the inverse, it's gonna cancel with 0. Equal 1, not 0, the identity. Now, if we multiply by the inverse, the left is going to be A, here is the inverse, D, P, okay?
Yeah.
But when you say that it's similarity, that's mean I can just move these here, it's the same. Okay? Now, you see, now we can find the D, the A to the power 10, because we have the inverse, we have P. Just the only thing we're going to do, A to the power 10 is going to be the P here, which is P inverse 1, 1, 0, 1, times D to the power 10. That's the important thing. Here's the D, 1, 0, 0, negative 1, but to the power 10, okay? And here is the P, which is 1, negative 1, 0, 1. D to the power 10, that means each element is going to be to the power 10. So A to the power 10 is going to be 1, 1, 0, 1. I'm going to write it down here. So then if we 1 to the power 10, this is 0, this is 0, this is negative 1 to the power 10. Times by 1, negative 1, 0, 1. So A to the power 10 is going to be equal. I'm doing these steps again, but we don't have to do it again. This one's going to be 1, 0, 0, 1. 1, negative 1, 0. And the result is going to be
It says a -1 to the power 10, it's just a -1.
-1. Because why? Because I don't have to put parentheses. So give me -1. The result is 1, -2. Is that the same thing we got? You're gonna get, I think, 2 examples like these. All my assignment. But you will see you're gonna do the whole steps. So here's the thing: when you do the test, if I give you like this example on the test, you see in each like you have the P, and you have to find the inverse. When you find the inverse, it's going to be long steps. Okay, so you don't have to do these steps. Just give me the inverse for this matrix. Go ahead, it's fine. Use the calculator to give me the inverse. I need to find the main steps. Then we'll go in details. Okay, because it's going to be like this is, you see, we don't find the inverse. If you need to find the inverse with details, it's going to be like 4 pages and takes a lot of time. Okay,